Have you ever stopped to think about the real magic your computer is pulling off every single second? I'm not talking about opening an app. I'm talking about running all of them at the same time. It's this quiet, constant miracle, and we're about to pull back the curtain on how it works. I mean, just think about what you're doing right now. You've probably got your browser open, maybe some music playing, a bunch of other stuff too. It feels like each one has its own little dedicated computer, right? But nope, they're all sharing one single brain, one CPU. So how on earth is that illusion even possible? Well, there's a fancy name for this trick, CPU virtualization. And the magician making it all happen? That's your operating system, the OS. The OS is this master juggler, right? It's giving each program a tiny, tiny fraction of a second on the CPU. And it does it so fast that to us, it looks like everything's happening all at once. But this whole act creates a really tough challenge for the OS. It's got to balance two things that are kind of at odds with each other. On one hand, you've got performance. We want our apps to be blazing fast, like they have the whole computer to themselves. But on the other hand, you have control. The OS has to stay in charge, making sure no single app goes rogue and brings down the whole system. So it's this constant tug of war, speed versus safety. All right, so if speed is what we're after, what's the most direct way to get it? Well, the simplest idea is to just let the program have the CPU. Let it run completely free. Let's dive into this approach, which is super fast and, as you'll see, super dangerous. This approach is called direct execution, and it's exactly what it sounds like. The OS just finds some memory, loads the program's code, points the CPU at the first instruction, and says, all right, you're on your own, go for it. And this is crazy efficient. There's no overhead, no one looking over its shoulder. The program is talking directly to the metal, running at full raw hardware speed. It really is the fastest way you could imagine. Sounds great, right? Super simple, super fast. So, what's the catch? What could possibly go wrong? Well, as it turns out, just about everything. Yeah, giving a program that much power is a recipe for disaster. First, there's the protection problem. If a program can do anything, what's to stop it from snooping around in another program's files? Or worse, what if it just starts overwriting critical parts of the operating system itself? And then there's the control problem. What if a program gets stuck in an infinite loop? It'll hog the CPU forever, and the OS has no way to step in. Your only option? The dreaded reboot. Okay, so clearly that's a no-go. We need a better way. We want that speed, but we absolutely have to have safety. This brings us to the first really brilliant idea that solves that protection problem, creating a kind of digital fortress. See, modern CPUs have at least two different modes they can operate in. First, there's user mode. Think of this as a padded, safe playpen. This is where all your applications live. If they try to do anything potentially dangerous, like mess with the hardware directly, the CPU itself just says nope. And then there's kernel mode. This is the VIP lounge, the control room. This is where the operating system lives, and in this mode, it has full, unrestricted access to do absolutely anything. This separation, baked right into the hardware, is the fundamental wall that keeps everything safe. Okay, that makes sense. But wait a minute, this raises a new question, right? If our apps are stuck in this safe mode, how do they do anything useful? Like opening a file, that's a privileged action. They can't do it themselves, so they have to have a way to ask the all-powerful OS for help. And that's where something called a system call comes in. It's like a secure, supervised doorway through that wall. Here's how it works. The app runs a special instruction called a trap. The moment that happens, bam, the CPU instantly switches into kernel mode and jumps to a very specific piece of code inside the OS. The OS looks at the request, does the privileged task for the app safely, and then, once it's done, it switches the CPU back to user mode and hands control right back. The program gets what it needs, but it never ever gets the keys to the kingdom. All right, cool. So we've solved the protection problem, but remember that other issue, the control problem? What happens if a program gets stuck in a loop and just never makes a system call? How does the OS ever get control back? Well, in the old days, systems used what's called a cooperative approach. They basically just trusted programs to behave. As you can imagine, that didn't work out so well. One bad program and the whole machine would just freeze. Modern systems are way smarter. They're non-cooperative. The OS doesn't ask for control back. It takes it. And the secret weapon for this is the timer interrupt. Think of it like an alarm clock. Before the OS lets a program run, it sets this hardware timer to go off in just a few milliseconds.
When that timer goes off, an interrupt signal is sent to the CPU, which forcibly rips control away from the running program and hands it right back to the OS, no matter what that program was doing. It's a guaranteed way for the OS to get its turn.
So, let's recap. We've got protection thanks to user and kernel modes, and we have guaranteed control thanks to the timer interrupt. Now that we have these two crucial pieces of the puzzle, we can finally look at the real magic of multitasking, how the OS actually switches between programs. This whole procedure is called a context switch. It means that when the OS decides it's time to run a different program, it has to meticulously save the entire current state of the program that's running, like a snapshot of its brain, and then load up the complete saved state of the next program that's about to run. So check out this incredible high-speed dance. Process A is humming along. Then, bing! The timer interrupt goes off. Hardware automatically saves a few key pieces of A's state and hands control to the OS. The OS scheduler says, okay, it's process B's turn now. It then performs the full context switch, carefully saving the rest of A's info and loading everything for B. And here's the clever bit. When the OS returns from the interrupt, it doesn't go back to A. It goes to B, which picks up exactly where it left off. And you want to know the truly mind-blowing part? This entire, incredibly delicate operation, saving one entire program's context and loading another, it all happens in less than a microsecond. That's less than a millionth of a second. It's an unbelievably complex and fast maneuver that your computer is pulling off all the time, completely behind the scenes. Okay, so let's put all the pieces back together and look at the big picture. Remember the goal? We needed both speed and safety. And this amazing combination of hardware tricks and smart OS design is exactly how we get there. You know, there's a really great analogy for this whole strategy. Think of the OS as baby-proofing the CPU. Before it lets any of the babies, our programs, run around and play, it first goes in and makes the room safe. It locks the dangerous cabinets, puts covers on the electrical outlets. It sets up all the rules and safeguards before letting anyone in. And here's the complete toolkit for that baby-proofed room. The user and kernel modes, those are the strong walls of the playroom. The system call traps, that's the secure little hatch where the baby can ask for help. The timer interrupt, that's the master key the OS has so it can walk in anytime it wants. And the context switch, well, that's the process of gently telling one baby it's nap time and letting another one come in for their turn to play. And when you put it all together, you get what we call limited direct execution. The direct part gives us that raw, blazing fast performance. But the limited part, enforced by all these clever tricks, gives us the total control and safety we need. It really is the best of both worlds. This beautiful, elegant dance between the hardware and the software. It's happening millions of times every single second that your computer is on. It's the invisible magic that makes everything you do possible. And it just makes you wonder, right? What other invisible tricks are happening just beneath the surface of the tech we use every day?